Hello everybody, this is Jimmy speaking. Welcome to my session. So today my session topic is data-driven processing designs. I will introduce how we use the advanced mathematical optimization method to improve the path flatness. So today I would split into my presentation into 4 parts. The first, I would like to introduce the both company, my customer, Interplex and the BASF. I also touch a little bit about our special service, Ultrasim. The second part, I will introduce the project scope, how we get it, and how we solve the challenge with an amazing method. The third one, when we found this really nice work method, we want to understand it more. And then after we understand it more, we also do the project recap with this method. And also we found some better solution that could be used for the other projects. Finally, I will introduce the summary and outlook. Probably we can expanding the usage for other projects as well. And also combining that the HPC technology, could give us really nice and cool solution in the near futures. And I would like also to introduce the team members here. Currently, I'm the speakers. I'm leading the project last year. So I'm the manager in BASF China. And also Helen is my team member. She's expert for plastics processing simulations. Also, thanks to her, she helped me to build the project from the scratch. And also, after I optimized all the parameters, she helped me to manually build the code runners and finally submit the report to our customers. I would like to touch a little bit about myself. I'm currently located in Shanghai. I joined BASF from 2007. My expertise is plastic molding simulation as well as structure and integrative simulation. Also, I will introduce later about the Ultrasim tools. I'm also doing a lot with these tools to help our customer for the business cases. I think recently with engineering getting more and more complex, I invest a lot of effort for mathematical optimization tools and also related to programming because you need programming to link different software together through APIs. And this is also, I would like to share a little bit about the mathematical ways to solve the problems. So for the introduction wise, I would like to give special thanks to Interplex because without their permission, I cannot really share the project here. They are the really nice partner that you can be reliable with them for cooperation. So let's talk a little bit about their company. I think they are the world leadings for the industry, and also they can provide you a lot of solutions for different part in the automotive. If you have really want to get some support from them, they will be really nice partner to cooperate with. And for BASF, I think these are listed some numbers just for reference. I also will not read through it. I think probably also you can search those kind of information from internet. Instead of that, I would like to introduce a little bit a different way from BASF. Besides of the material supplier, we also provide a lot of support for our customers, especially for simulations. We have our simulation tools we call the Ultrasim. This is where we base our know-how on our material, and then we combine the material know-how and the customer design and processing expertise together with a package that we offer to the customers. I think the advantage with these tools, they can bring less prototyping time and less cost. Also, you don't need too much prototyping needed. Ideally, just one prototype for testing, that would be enough. A lot of our customers, especially in automotive, they already tried and success with it. Not only from automotive recently, we also get a lot of projects with furniture, appliance. We also do a lot of support for them. I think we'd like to introduce a little bit about the Ultrasim. What's that? For Ultrasim, basically there's two parts. The left one is the material modeling. And because if you look at the engineering plastic reinforced material, they are pretty complex material. First, they are anisotropic, they are nonlinear, and they are strain rate sensitivity. And if you count all those kind of complex things together, you need really a nice material model to describe it. So we made our own material models. This we call the calculate the part right. This is accurate modeling, but for simulation target, it's not really to replicate the errors what happened in the real life. We also need to optimize it and improve the design. So we have the right part, we call the calculated right part. The parameter optimization is one of the part that inside of the right way we provide to our customers. So if we combine them together, we could do the right things right. According to injection molding, we do a lot of support for our customer. We do mold fillings, we do fiber orientations, mold cooling, and the shrinkage warpage by one of the tools here. I think everybody knows Autodesk Moldflow. We help our customer to solve it with it. And also, we will have a nicely built material data. It's high quality measured. So beside with this kind of material data, our customer can also modeling the injection molding very nicely, accurately. Not only our simulation machine, you can also do it by your own. And this is I showed some successful cases before, especially in automotive industry with our Ultrasim support. I think there's a lower bumper stiffener, engine mounts, and also we have appliances like a seating and other like pedal brackets. So this is our customers' examples. We did it before. So let's back to the project itself. This is the part we'll show you here, and also this is the final solution we get to our customers. So let's get back to that history. Well, what we get from the project from starting point. So this is the part I get. This meshed covers. The length is around 550 millimeters, and this is a pretty long part. The problem is the part is not really continuously. There's a lot of meshed holes. They can make the injection molding not that easy. But our target is just make the part as flat as possible. Our challenge is if you just put the gate in the two sides, which is get from experience, you will encounter very high injection pressure. That's make the solution impossible. And also, if you put the gate and using sequential gate solution, the problem is this is too many gates. You need a lot of hot runners and the valve gates. They also will bring additional cost. This is also not really favorable solutions. So basically, the customer, they would like to have multiple gates, but still use cold runners with limited cost. So this is a really challenge it came from. So they ask us whether can you work on that. We see, okay, maybe we can have a try on that. So first, we would like to see what the problem looks like and the real complexity. We first initially designed with 12 gates. So this is based on experience levels. I think that we just evenly distribute inside of the surface. And of course, can see that the result really looks not that really nice. The Z warpage is 8 millimeters. If you compare to the 550 millimeter for length, this warpage is pretty big. I think maybe even you mold it, the actual warpage could be even bigger than the simulation. That could be cause a lot of trouble in the later assembly access. So I just want to show the final result we get with this cool optimization method. After 36 iterations, we get very different out-of-box design. You can see the flow pattern is from outside to the inner. And the amazing things, they just reduced the warpage from 8 millimeters to 4.5. I think almost half. And this whole running is through the 3 days, because at that time we have 2 days of a weekend and plus one public holiday. We went back to the office on Monday. I saw the result looks amazing. So this is out of my expectations. So how we do it? This is my optimization setup. I divided the part into 4 regions. Each region allows 3 gates. The gates can be moved freely in the y direction. I also set up the small overlaps. That means the gate 1 and gate 4, they can be concentrated into small areas. Sometimes manually we can merge them into one gate. And this is the design of that. Allow some kind of freedom for reduce the gate numbers. I use iterative approach, but it's sequentially, not parallel. I use the solver or optimizer from the Empower Operations. Also, thanks to this company. I think this is a Canada company. They have really nice optimizers. They can do a large number of optimization within limited iterations. So I just run 36 iterations. I cannot say this is the best answers, but from designer point of view, this already a very nice result that could be used for engineering point of view. So after I get the gate location from the automatic calculations, I found these two gates are pretty closer to each other. We decided to merge them together. And Helen helped me to rebuild the rounders. This is the very unsymmetrical rounders. They just flow the pattern from outside to internally. After that, we checked the result from this setup. We found to give us really nice warpage by this setup. So this is a summary of the project running at that time. I found that when we set up with proper program, everything can be run automatically. I don't even to worry about during the whole weekend. But of course, I check and monitor some jobs during that time. At the weekend, it runs smoothly. And the final solution is quite out of my expectations. I don't think you can get this kind of result by someone's experience because it's pretty complex. I think that because of the complexity, I think the mathematical tools are much powerful than human can handle this. I think this is very helpful for those kind of complex problems that can be handled. So what is the benefits for the optimization? I think we learned from the project is to kind of give us amazing result, but we also want to understand why it came from, how we can use it more for other projects. So we learned a little bit about the mathematical optimizations. So this is the explanation from Wikipedia. I think that the optimization, this concept already, I personally think it is already overused by a lot of persons and a lot of papers. I think that, for example, if you for simulation wise, if you're just using the one result and then improve it, and then someone will call it optimization, but it's not really mathematical optimization. What mathematical optimization is, they have a very special target, so they would like to get the best result through certain designed iterative approach. So, for example, this is a function here. If you want to get the minimum level, if you just do blind search, I think maybe you can still find the answer, but it takes a really long time. But the mathematical optimization, the difference is using the design iterative. They have certain kind of strategy to do it. Then with this strategy, you can save a lot of time and to get those results. Of course, you can describe the problems by mathematical ways. So you can describe the function. This is target. You can input a lot of vectors, like we call the parameters, to get the function 1, function 2. It can be also multiple function, whatever you like. But normally we do not use multiple function because just increase complexity. For these problems, I will use it for is a single object optimizations. We do not introduce the constraint from expensive restraint. For that problems, we only use that the gate allocation limitation that they cannot move into some space, but we do not use some other expensive constraint like injection pressure. Why it called constraint expensive constraint? Because this constraint cannot using the simple mathematical equation calculated from the parameters. We have to get the constraint value from the solvers. That means we have to run the Moldflow and wait for 3 hours to get the maximum injection pressure. So this is quite a lot of effort to do it. So we call it expensive constraint. So this is a mathematical function to describe it. Basically, this is a little bit boring. So thanks to Dr. Gary van der Platz, they also have cartoon ways to describe it. We can imagine this is a design space, we want to get it. And this blind man here is walking inside of it. This is fence. You can not walk out of fence. This is a limitation. We call it constraints. I think this guy, they can just touch it, the ground by his feet, and they will feel whether the next step is higher, lower than current position. You can see this lady, and he guides this guy going to the position we call optimizers. If this lady can saw the red flags, the position, that means this is not really black box problem. I think that's much easier to solve. They can just guide the guy into the position easily. But if the ladies can also not see the flags, we call black box problems. That's really purely based on this guy's feedback of data to this lady, and this lady have to decide next step just based on the points of that what the guys get. I think this is a real problem, engineering problems we are solving almost every day, because we cannot really get a fully understanding of this design space. We just know some space points. So this is I think this good explanation about the actual problems by optimizations. Why we need mathematical optimization? I think that because our daily working problems is pretty complex. If you look at that, our input and our output, they're really like a box with lots of cables inside of it. You cannot really find out which cables connect to which and how big influence of that. So you need basically tools to solve that. Then we can introduce mathematical optimization tools to do that. This is one example which BASF introduced in the 2014 Moldflow user meeting in European. This is a fiber orientation prediction by the optimized fiber parameters, which is introduced by my colleagues Andreas Warnisch. You can see the default parameters of fiber orientations is still a gap compared to the CT measurement. After optimize the fiber orientation parameters, we can get much closer to the CT measurement. After you press the part with the right parameter of optimize the fiber orientation, if you compare the test, they can also get the right pattern of the failure. This is also quite important for the integrative simulations. At that time, we're already using the optimization ways to get the fiber orientation parameters to get a better result. So for optimization algorithm, there's two ways. One is gradient based, the other one is gradient free based. The gradient based, they need the function to be continued. I think that they just get the gradient of each point, and when they found the gradient going to 0, they said that we are already at the target. The problems of gradient based, they are very easy to trap into the problems, something like that. If you have a right side the picture, it shows if you have an initial starting point into some valleys, then you are easily trapped into the very local minimum value. You cannot really find the global minimum values. So this is the shortage of this gradient based. I think that for this case, we're using the gradient free method for the next approach. Because we are not really sure the problem looks like. So we would like to use the global search method to find the minimum values. So the project recaps. After we got the understanding of the optimization method, we also do the recap of the project. For last one, we managed to reduce the warpage from 8 millimeters to 4.5. I think this is almost half reduced of warpage. But if you look at the injection pressures, the pressures increase about 50%. The pressures from 80 megapascal to 120. At that time, I don't think there is a problem to mold it, but we still would like to raise the questions. Can we reduce the warpage and keep the injection pressure low? So we take this question into another round of optimizations. So this time, I set up exactly the same, but I add one constraint. I ask the solver, please keep the maximum injection pressure less than 120 megapascal. So I still using iterative approach, but this time I'm using the genetic algorithm but not the commercial software. And then I will ask the generic algorithm to check each answer whether it violates the constraints. If it is violate the constraint, I will throw away the result, even the warpage is very nice. And then I use this warpage, this algorithm, to find the best gate location of the plan. So I think that the problem is pretty complex, but maybe you do not know how complexity from quantity level. Let's just show you the complexity from some data points I know. I think there's 12 gates positions with y-dimensional freedom for optimizations. For each gate, if we're just using 3 variations, the highest value, the lowest value, and the middle value for each gate, then we have 3 power of 12. That equals around 500,000 cases we have to run. As I mentioned, each case will take around 3 hours. So probably you need 180 years for the calculation time. Even with super high level computers, you can run the simulation like 100 cases simultaneously together. We still need 1 year. I don't think the customer can wait that long to get the answers. So basically, this blind search is not really a good way. Then we find out we need some algorithm. This complexity cannot really solved by blind search. You need a certain kind of mathematical approach for that. So that's why we found the generic algorithm. I think the generic algorithm is quite bio-based method. This is I think everybody knows Darwin has evolution theories. This is very similar to that. For the loop, you first initializing the population from the coverage. For example, you can initialize 20%, 20 cases, 30 cases, or 100 cases, just based on your calculation capability. And then you calculate each fitness function. Fitness function here means warpage for our cases. Then I think that for 100 cases, for example, then they can choose the best one. You can choose 10%, 20% based on your settings and do selections. And after selection, you choose the best answers and to exchange the genes and parameters inside. We do reproduction. Something like if you have a good answer A and a good answer B, they can produce another answer C. They use half of the parameter from A, another half from B, or either way around. So this is called like the offsprings. The offspring could be maybe have better result even than your parents, maybe even worse. So that depends on the situation. So evolution is like they choose some best one and reproduce with more offsprings, and from more offsprings they also choose the best one. So basically you can have answers better and better by generations. So this solution can be looped until you think that the result is good enough. I think they have pretty a lot of advantage. Most biggest advantage is it can be parallel, because when you initialize the population, it just depends on your hardware numbers and license numbers. You can just, for example, if you run 10 simulations together, you can have 10 simulation result after 3 hours. So it's pretty nice if you have a lot of license and hardware. And then also disadvantage is also that you need a very big computation power, and also the model is not easy to be tuned. You need a lot of experience understanding this algorithm to tune the models. So this is need a certain level of understanding. For these cases, I run another 376 iterations. This is a lot. It cannot really finished in 3 days. I just use it for kind of research. So I set up of constraint of maximum 120 megapascal. I found in the final result, 65% they can meet the requirement. They call effective solution, which is they can meet the constraint. But another 35% they cannot meet the constraint. They will be abandoned. I found that among these iterations, there will be 2 results could be good candidate. I think this one is just a little bit higher, like 5% higher than the warpage we get before. but they reduce the maximum pressure into the range we want. The another one is we have 10% higher than the original one, the last best warpage, but they can reduce the pressure almost close. They're just 10% higher than the original one. I think this is a very nicely result compared to the other things. If you don't have a big injection machine, this could be a very good answers. Okay, I show the picture of the boxes that was input and output. Now you can see this real problem looks like. You can see this is the input arrays from G1 to G12, and then I did use the relative value. This is normalized, and then if you look at how the connection to the Z warpage, it's very hardly to find the values, how to how tidy the date. Also for here, I also filtered the result, which is more than 120 megapascal, but you still can find some kind of rules. For example, you can look at the G6 and G7. The lower value of G6 and the G7, the higher value of G7, this combination, they probably will get more green lines. The green lines here means low warpage. The red lines about the path with a high warpage. I think that probably through some data mining tools, you can find some that a better solution by this also interactive way. So this is the final solution I get from the constraints. I think that the warpage from solution 1 and the warpage from solution 2 is pretty close to each other. The only difference is that the maximum pressure they can reduce a lot. I think for the solution 2, we can also here combine the gate here and here. We can even reduce the gate number from 12 to 10, but we can still keep the pressure in the similar levels. This is the result I get from that. I think if we get the result later, probably our customer will choose that solution. But basically, they need a long time to wait for the result. Let's see the summary and a outlook for the futures, just like the kids shows. I think the future is coming, and in the later, the future is totally different. It could be with our current solution. I think for this time, I solve the problems not really based on experience. I based on data. So the data is just generated by the mathematical optimization tools. The advantage is with such kind of big amount of data, the mathematical optimization can bring us totally out-of-box solution. Also can be very nicely fit for our target. And then when they exploration the design space with more result, they can also provide us better understanding of the problems. For example, if you have 300 of data points, you can think about to rebuild the meta models to describe your problems. I think through the meta model, you can find even better answers and also help you to understand the problems looks like. I think that you don't need to really worry too much about hardware in the future. I'm pretty sure that in the near future, there will be like several hundred cores just in one CPUs. So with this multiple core, you can run more simulation together. I think hardware will be automatically solved by some guys. But the challenge will be that if you really want to run the simulations, you need really a good guy to understand the programming, because software cannot talk to each other. You need a kind of API tools to link them together. So you need some guy to do the programming, tell the software connections. And of course, the hardware and the software license could be a kind of issues. Although if you do not have enough license numbers, even have very nice hardware, you still need to wait a long time. So this is my wish to Autodesk. I know the Autodesk already have the Amazon cloud solution for DOE, but they cannot really solve the problem looks that I showed today for the gate location optimization. They still need some the tailored way for programming and API connections. I hope they can provide us special type of license which can allow us to do more cases for those kind of optimization. I think with that, we can use it to solve the problems much quicker and provide additional value for our customer. And I hope, I also think there will be benefit for all of us in this environment. And this is our wish to them. Hope it works. Okay, this is all the presentation I would like to show you today. If you have some problems, you probably can contact the guys from Autodesk. I will try my best to answer it. Thank you very much.